I'm going to be talking about how some fast algorithms can be made more expressive and interpretable by adding regularization. Just to give you a roadmap for what I'm going to be talking about today, I'm first going to review the topic modeling problem. I'll give a brief overview of a very fast new approach for solving this problem, and then how we can improve that by adding regularization. We'll show that adding this regularization can sometimes, but not very often, improve held-out likelihood, improve dramatically the interpretability of the topics that you get out, and allow you to do new things that you weren't able to do before with these approaches. At the end, I'll talk about why some of the things that we tried didn't work so well, and what we're going to try next to do a better job. So first, let's review topic models. So the topic modeling problem is you have a bunch of documents and you want to have a summary of what's going on in those documents. The output that you get from a topic model is a set of words called topics that explain what's going on. And these topics is a distribution over all of the words in your vocabulary. And the topic modeling problem is to figure out, for every word, what is the probability of that word given the topic. Now, most of the time, at least today, when you think of topic modeling, you think of probabilistic Bayesian approaches. And these work relatively well, but sometimes they get stuck in local optima, and they don't always scale well to very large data sets. Recently, a class of new algorithms have come out that are very fast and can provably reach global optima, but they don't always find the best topics. And we'll say in a second why we think that adding priors might help these methods improve. And they also haven't been subject to the same scrutiny in terms of evaluation techniques that the more established probabilistic models have. We're going to focus on a technique called the anchor algorithm by Rohr et al. And it's very attractive because if you look at how it scales as you get to millions of documents, compared to traditional techniques like Gibbs sampling, which scales nearly linearly, the anchor algorithm is basically a flat line. Where it doesn't do so well is that the topics it finds sometimes includes these general words like people, make, things, that when compared to what you get from more traditional approaches could be replaced by much more specific, relevant words. And at least in the probabilistic models, this happens because we have priors that encourages sparsity in the topics. And adding a prior is akin to regularization. And what we'll show in this work is that when you add regularization to the anchor algorithm, you can get topics that look quite a bit like what you get from these more traditional approaches. But first, let's talk about the foundation of our approach, the anchor algorithm from Rohr et al. 2012. One of the great things about topic models is that it finds polysemous words that occur in many different topics. So for example, the word run can appear in topics about baseball, soccer, and elections. The great idea of topic modeling using the anchor algorithm is that the anchor algorithm find so-called anchor words that are unique to a topic. So if you see the word shortstop, you know almost certainly that you're talking about baseball. If you see the word offside, you know almost certainly that you're talking about soccer. If you see the word voters, that means that you're almost certainly talking about elections. Another nice benefit of anchor words is that they serve as a handy shorthand for talking about topics. So for the rest of this talk, whenever I refer to a topic, I'll use the associated anchor word as its label. Now, finding anchor words is a hard problem, but we're not going to address that. We're going to assume that we have anchor words provided to us by the very clever algorithms developed by Aurora et al. And this is nice because once you have the anchor words, it's fairly easy to find out what the topics are. Now, in particular, what we're going to be doing is a little bit backwards from what typically happens in probabilistic topic models. So in probabilistic topic models, you usually find the probability of a word given a topic. We're going to be going in the other direction. We're going to be looking for these topic coefficients C that are the probability of a topic given a word. But it's fairly easy to flip this around using Bayes' rule. Figuring out what all of these coefficients are is fairly easy if you know what the anchor words are. And again, we're assuming that this is given to us a priori. The anchor method is so efficient because it doesn't look at all of your documents, it only looks at a matrix that is V by V, where V is the size of your vocabulary. And this matrix is filled with the conditional probability of words. What's the probability of seeing word J given that you've seen word I in a context? And if you look at the co-occurrence probability for an anchor word, like shortstop, that looks a lot like the topic distribution that we're interested in. Because once you see shortstop, the other words that you're going to see are going to be a lot like what you'll see in the baseball topic. Now things get a little bit more complicated for other words that are polysemous. So for example, consider the conditional distribution of words given that you've seen the word fly in some context. Now you might see things like airplane and bug and catcher and Yankee. Why do you see those words in contexts that include the word fly? So part of that might be that you have some aviation topic with the anchor word Boeing. That explains some of what you're seeing. You might have some topic about insects with the anchor word insecta. And you might have a baseball topic too, explaining some of that distribution. And if you add up all of these things, you can get the conditional distribution over words, given that you've seen fly in the context. So it's a linear combination of the conditional distribution of words given various anchor words. What are the coefficients? These are the topic coefficients. The probability of seeing a topic given that you've observed some word. And these are the CIKs that I talked about before. And from these, we can get the traditional topic modeling output, the probability of word given a topic. But this toy example doesn't tell the whole story because there are lots and lots of anchor words, at least dozens, possibly hundreds. These anchor words can be thought of as a convex hull of a very high dimensional space of conditional word probabilities. And so you have some set of anchor words, and it's a relatively large set. How do you, for any arbitrary word, combine these anchor word distributions to explain what's going on with the word fly? So you have to combine up all of your anchor word distributions to approximate as best you can what's going on with the word fly. And where regularization can help is that, hey, you don't want to use that many anchor words to explain a particular word's context. All else being equal, you should use only as many as you need. So that's the idea behind regularization. Let's go to the first form of regularization that we're going to talk about, L2 regularization. So the traditional anchor objective function is to choose topic coefficients that get as close as possible to your observed word distributions in terms of the Kale divergence between these two distributions. All we're going to do is add in an additional term that says, don't let your topic coefficients be too large. So if mu is 0, that corresponds to a Gaussian prior with mean 0. And this is saying, okay, try to make your linear combination of anchor word distributions match as well as you can your target distribution for any particular word in your vocabulary, but try not to make CI large unless you absolutely have to. So we evaluated this method on 3 data sets where we fit our topics on the training fold, we choose hyperparameters on the development fold, and then we report metrics on the test fold. So the first evaluation that we did was held out likelihood. How well does the topic set that we discovered generalize to new data that the model hasn't seen before? So what was surprising to us is that in some cases, it helps. For example, when you have a very small data set or you choose your hyperparameters poorly, you can improve the held out likelihood, but it's fairly rare. So this was a bit of a wash. It didn't work as well as we expected. But what L2 regularization does allow you to do is it lets you do things that weren't possible before. You can have more expressive models. So for example, you can set the mean of your L2 regularization to be something other than 0. So for example, if you have some prior knowledge that the word piece should appear in specific topics, you can encourage that to be associated with the right anchor words by setting the mean appropriately. So set it higher in the case that you want it to be associated with those anchor words and 0 otherwise. So we use as a source of information about what words should be associated with what topics, aka anchor words, the linguistic inquiry and word count from Pennebaker and Francis. And so you have some set of anchor words, and we can see which of the Luke categories line up with those anchor words. And for the set of words in Luke that it says should be associated with Soviet, we increase that mean. So what we get out of that is that Luke associated Soviet with military-related word. So that brings in things in the Luke dictionary like military service, army, chief, troops, officer into the topic, but also things like nuclear weapons, a specific kind of military device that wasn't specifically mentioned in the Luke dataset. And similarly for the peace anchor word, it brings in things like offer, justice, aid, deserve, replacing the military aspects of the negotiations with Israel to focus on Bush and Clinton who tried to broker two-state solutions. We also used another form of regularization that we call beta regularization. So typically in topic models, we assume that each topic comes from a Dirichlet prior. Because of the formulation of anchor words, we can't do that directly, but we can use individual one-against-all beta distributions that simulate this Dirichlet prior. This is possibly because of the marginal consistency of the Dirichlet distribution. So this gives us a new objective function that looks like this. And we evaluated this using topic interpretability, which is a method that correlates well with human evaluations of how good a topic looks. And so higher is better. So if the topic interpretability score is high, that means that a likely outcome is that a human will look at that and say, yes, that makes sense as a topic. So this almost always helps topic interpretability, adding the beta regularization. And so why does it help the interpretability? So what happens is that the anchor method tends to bring in these very generic, vacuous words, like people make things true, and adding in this regularization pushes those general words out and encourages more specific, relevant words to come in instead. So for example, in the God anchor word topic, sin, Christianity, atheist, peace, heaven are brought in instead. And not only is the regularized anchor method using the beta regularizer doing better than the vanilla anchor method, in some cases it's competitive with more traditional implementations like MCMC or variational inference. That's the good news. The bad news is that it still doesn't help held out likelihood. So I want to spend the last few minutes that I have talking about some of these issues and why we didn't do so well on held out likelihood. So there are a couple of things going on here. One is that selecting the anchor words is very important. And if you do a bad job of selecting the anchor words, regularization can help more. But if you do the things that Aurora and all tell you to do in the paper to select the anchor words, such as only allowing anchor words that appear in some set number of documents, say 700 or so, that has a huge impact on the held out likelihood. And what we think is going on is that this process of selecting anchor words is providing some sort of implicit regularization. The other factor that's going on here is that we're assuming that we know what the anchor words are. And once you have a fixed set of anchor words, that really constrains the models that you can discover. So regularization can help, but it can only help so much because you're tied into using a very small range of models. Another issue that's going on here is that held out likelihood and what topic models are used for are in tension. So topic models are used for exploring data sets, and people pore over the top words of a topic, but the words that really affect what happens in held out likelihood are at the bottom of the topic. So these issues are in tension, and as discussed in the Reading Tea Leaves paper, what goes on with held out likelihood is often unintuitive, and models don't give you a good trade-off between these two competing goals. So what we'd like to do in the future to address these a little bit better is to select anchor words based on additional knowledge, to do a smarter job of selecting anchor words that can accomplish some of the things that we accomplish through priors or regularization. We think it would also be helpful to use regularization techniques that induce true sparsity using the L1 or L infinity norms. We were scared off of this initially because of the non-differentiability of the resulting objective functions. In addition, using regularization and other very fast techniques would help, such as power iteration or the novel word algorithms. And hopefully we can use these techniques to have the best of both worlds, to have the speed of these very fast methods with the same expressivity and interpretability that we have grown to expect from probabilistic models.